Good day, viewers. I want to welcome you to today's class on linear regression, stroke linear curve fitting. We shall be looking at how to fit a straight line. This topic is a topic that is useful in statistics, and it is also useful in numerical analysis. In numerical analysis, there is a topic called curve fitting, and curve fitting is divided into two parts: linear curve fitting and non-linear curve fitting. So in one of our videos that will be coming up, we'll be looking at non-linear curve fittings, but today we shall be looking at linear regression analysis stroke linear curve fitting. These two topics have 100% relationship and similarities, so that's why I've come to combine them today. And this is the model of a straight line. This is a straight line model. Y subscript C means the estimate of y is equal to a plus bx. A and b are constants. Once again, beloved, I welcome you to my YouTube channel. My name is Dr. Chris Esekaigbe. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I live in Nigeria and I work in Nigeria. The chief lecturer position is the peak in the polytechnic system in Nigeria. And by the grace of God, I attained that position in January 2023. Please subscribe to my YouTube channel, Dr. Chris Esekaigbe. The essence of this channel is to share knowledge across the globe on topics that are interesting in mathematics and statistics. That is the essence of my YouTube channel. Please subscribe to my channel, share my videos on your social media platforms, click on the notification button so that anytime I upload a new video, you will be part of those to have a notification. God bless you as you do that. I hold a doctorate degree in mathematics, a master's degree in mathematics, and a bachelor's degree in statistics. What a blend. What a blend. I am a specialist in numerical analysis. I also do a lot of data analysis and modeling. You can consult me with your statistical research. I do statistical research, scientific computing, even mathematical computing. I will be glad to have you around. I will be glad to work with your team of numerical analysts. What a blend. A statistician and a numerical analyst. What a very good blend. And today's topic is fitting a straight line. And that topic is under linear regression in regression analysis, and it's also under curve fittings in numerical analysis. Please, if you want to contact me with your research work, if you want me to be part of your team, maybe you are a research institute across the globe, you do a lot of research, you do a lot of analysis, why not? You can contact me to be part of your team, whichever country, English-speaking country. I speak English fluently, I do my job. I speak English language, I do my job speaking English, writing English. So you can contact me wherever part of the world you are. You can contact me to work with you as a team in the area of numerical analysis, in the area of data analysis and modeling. I'm also a data scientist, having obtained a BSc in statistics, and I've undergone several training in data analysis and modeling. My contact numbers are +234 80 330 21903, and the second contact number is +234 7066 297535. Both numbers are WhatsApp numbers. You can call me directly on these lines, you can send a WhatsApp message to the numbers, and my email address is chrisdavids2015@gmail.com. I've written quite a number of books in numerical analysis and statistics. I have a book that I authored, a first course in numerical analysis. I also authored 2 books in statistics, applied statistics for business, sciences, and engineering. I also authored a book in trig and functions and geometry for undergraduate, mathematical methods for undergraduate, linear programming for undergraduate. So please contact me. If you are an AI firm, I can also work with you in developing advanced mathematical models or algorithms for artificial intelligence. I will be looking forward to hearing from you, to meeting you, to speaking with you, so that we can go ahead with the research. Or you are a researcher, you need statistical analysis, or you are a research institute, why not consult me? Or you are a university or a polytechnic or a college that you require somebody that will be part of your research team or the work you are doing, why not contact me in these numbers? As you do, I will be privileged to work with you as a team. God bless you. Once again, subscribe to my channel, Dr. Chris Isekaibe. Click on the notification button so that anytime I upload a new video, you will be part of those that will have notification. Share my videos on your social media platforms. As you do, God will bless you. Now we want to go quickly to the business of the day. Permit me to clean this contact on the board. I'm a member of the Nigerian Mathematical Society. I'm also a member of the Nigerian Statistical Association. God has helped me to build myself in these areas over the years. Now, linear regression / linear curve fittings. Now, linear curve fitting is a topic in numerical analysis, while linear regression is a topic in statistics. Both of them have to do with the fitting of a straight line. What a blend! A blend of numerical analysis and statistics. A blend of numerical analysis and data analysis. As a data scientist, as a data analyst, and as a numerical analyst, I will be glad to bring you the relationship between or among the various topics in these two subject areas, the relationship that they have and the differences that they have, and how we can blend them together. You can see me blending a topic in numerical analysis and a topic in statistics to teach today. It's as a result of my vast knowledge over the past 20 years in the teaching of mathematics and statistics courses. Thank you once again. Please stay patiently to the end of this video as you watch. Now, when we talk about regression analysis or linear curve fitting, what does it mean? It means finding out linear relationship between two variables. When it is linear, it means you are finding a linear relationship between two variables. Now the variables here are x. X is known as the independent variable, and y is called the dependent variable. That's why you can see it, y equal to a plus bx. A and b are regression constants, or you can just simply call them constants. A and b are simply regression constants or constants that must be solved for. The essence of regression analysis is to help us do estimation, is to help us do prediction, and it is also to help us do forecasting. When you have this model will help you to predict, to estimate, and to forecast. And you know, one of the vital purposes of statistics is to forecast, is to predict, is to estimate. And these help you a lot in planning, in organizing, in quality decision making. So when you have a set of data and you bring out this model, it will help you to prepare or plan into the future. Get a model or get values, get estimates that you are expected to see in the future, and you plan towards achieving them. So now our A here from this linear model is called the intercept of y. A is called the y-intercept. A is called the y-intercept. In this value of A indicates the height on the vertical axis. It indicates the height of the vertical axis from where the straight line generates or originates, representing the value of y when x is 0. Now there are two methods that we can use to fit a straight line. Number one is called the freehand drawing method. Freehand drawing method. And number two is called the least squares method. So now the freehand method requires you drawing a scattered diagram in a graph. A graph will have the vertical axis, which is the y-axis, and the horizontal axis, which is the x-axis, and the data set. Of course, you will be given two data sets in x and y. They will be plotted in a scattered diagram. Then a transparent ruler will now be used to sketch a straight line. A transparent ruler will now be used to sketch a straight line. Remember, I told you our A here is the y-intercept, YB is the slope. B is known as the slope of the straight line. Slope of the straight line. B is the slope of the straight line. YA is our intercept. A is the intercept. A indicates the height on the vertical axis. Now when we talk about the freehand method, you sketch a graph, maybe a graph of this nature. This is the x-axis, that is the horizontal axis, this is the y-axis, this is the, then you now have some scattered points, scatter diagram, and so on and so forth. Then the essence, you try to draw a straight line with a transparent ruler. A will definitely, where the particular straight line starts from, A will definitely attain that particular value. So A will now indicate the height on the vertical axis from where the straight line originates, representing the value of y. It will represent the value of y when x is 0. So you can imagine this: when x is 0, it means that this particular quantity here will be 0. So y will now be equal to A. So when x is equal to 0, then our y estimate will be equal to A, and that is the intercept. But now when using the freehand method, the drawback of the freehand method is the simplest method. Just like plotting the normal graph, then you are able to use a transparent ruler to sketch a straight line. The challenges here is that the slope will differ from person to person. It may not be easy to get the slope, and when the slope is not easily gotten, the slope B shows the absolute change in y for a unit change in x. That is what the slope B does. A little change in y for any change in x. So it shows the absolute change in y for a unit change in x. This simply means that the slope may be positive or negative. It indicates the nature of the relationship between y and x. So this slope B, this value of B, is what indicates the relationship, the nature of the relationship between y and x, the two variables y and x. Now, if you look at this, if the slope is negative, it means that the independent variable x will impact negatively on the dependent variable y. If the slope b is positive, it means that the independent variable x will impact positively on the dependent variable y. So a unit change in x, or it shows absolutely the change in y for a unit change in x. The slope, it may be positive or negative, and that is what indicates the nature of the relationship. Note, a relationship can be positive or negative. If it is positive, if for instance, if the relationship is positive, if the slope is positive, that means if as x is increasing, y is also expected to be increasing. But if it is negative, that means it's going to show a negative impact. X is going to show a negative impact on y. So hence a and b can be computed using the least squares method. A straight line is completely determined by its intercept and the slope. So without the slope b and without the intercept a straight line cannot be determined. So the least square method involves the derivation of what we call the normal equation. Then with the help of the normal equation, we will now be able to calculate the values for a and b. We'll be able to calculate the values for a and b. I hope this is taken. Now permit me, I've explained the free Android method and the least squares method. We will now be seeing how we can generate our normal equations using the least squares method. Permit me to clean this. So now we are going to see how we can generate the normal equations. Now, if we have y is equal to a plus bx, this simply means you are regressing y on x. That means y is depending on x. Permit me to share the body into two parts. If I have x is equal to a naught plus b naught y, this simply means you are regressing x on y. Now, for this particular model, this is a straight line model, it means y is depending on x. I told you from the beginning that the variables must be two. The variables here are x, y and x. The one on the right hand side that is multiplying the slope is known as the independent variable, while the one on the variable on the left hand side is known as the dependent variable. Here, for this particular problem, our x is independent variable, while our y is dependent variable. Then here, our x is dependent variable. Then here, our y is independent variable. You can see that. So this one is x on y. So here, our intercept is a naught. We use something different so that we can distinguish between the one regressing y on x and regressing x on y. So we are using a naught and b naught here as our constant. Here we are using a and b as our constant. So you can see the variable multiplying the slope is known as the independent variable. Here our independent variable is y, while our dependent variable is x on the one on the left hand side. Here the variable multiplying the slope is, because the slope is what determines the nature of the straight line. It determines the nature of the relationship, whether the relationship is going to be positive or negative. So b here is the slope, and the variable multiplying the slope is the independent variable. So x is our independent variable, and here our y is the dependent variable, the variable on the left hand side of the equation. Now, I want to show you a very simple way of generating the normal equations without going through any rigorous process. Now, our normal equations. Very simple. You get the normal equations from the model. This is the model. It is the model that determines the normal equation. What I do, I sum. The first thing is to sum the model. How do I sum it? I will have summation y. Is it because it runs from the number of data sets. Of course, we will have the number of observation. So we sum it from the first observation to the last observation. So that's why you are summing y, which is the variable, from I is equal to 1 to n. So then, if you sum a, of course, a will be an. That means the number of times you have that. That means a will be in n times, then plus b summation x. So you have taken the sum of the model. You can call this equation 1. Then the next one, you do something to this. You multiply this first equation by the independent variable. Our independent variable here is x. So you use it to multiply this equation 1. Multiplying equation 1 by x, you have summation. This becomes summation xy is equal to a summation x plus b summation x squared. This becomes equation 2. So now, these are the two normal equations generated from this model. Now, this will now lead us to a set of simultaneous equations having two unknowns in two equations. The two unknowns are a, b, a, b. Now, if you come here to the case of x on y, our normal equations from this same model. So you take the sum first, like we did here. When you take the sum first, we're going to have summation x is equal to a naught n, or n a naught, plus b naught summation y. This will now be your equation 1. Then now you multiply this equation 1 by the independent variable, not the dependent variable. So if I multiply this, my independent variable here is y. If I multiply this by y, I'm going to have summation xy is equal to a naught summation y plus b naught summation y squared. Y by y is y squared. This will now be your equation 2. So when you are looking for, you want to fit a model, a straight line of x on y, you are going to use these two normal equations to get your constants, a naught and b naught. And when you are fitting a straight line or a linear curve having this model where a and b are the constants, a is the intercept, b is the slope, these are the two normal equations you are going to use to get your constants, a and b. So now, permit me to pick up an example. Now, when you say a and y depending on x, y is a variable, y is used to represent a particular set of variable, yx is also used to represent a set of variable. Now, if for instance I say, is it possible for students' attendance to be dependent on their performance in examination? Of course, yes. So students' performance in examination can depend on the number of times or their participation in class work, attendance to classes. Also, can my income determine my spendings, my level of spending, or my level of expenditure? Yes, of course. Because I cannot spend more than what I have. So my income can definitely my income can definitely determine my expenditure. That means my expenditure, my expenses is highly dependent on my income. So that's why you can see, if for instance if I now say let income income be X, then let expenditure be Y. So you can see that my expenditure will definitely depend on my income, because no one can spend what he or she doesn't have unless you want to be living on borrowed life or buying things on credit and the rest of them. But if you want to spend according to your income, of course your spendings will definitely depend on your income. So you can see here that the income is independent, will not be there. So you are now going to fit Y on X, expenditure depending on my income. Likewise, examination performance depending on students' participation in classes, students' attendance in classes. So note, for this particular topic, we are dealing with linear regression. Regression in general has two types. We have the linear regression and the multiple regression. Likewise, curve fittings. Curve fittings has two types. We have the linear curve fitting and the non-linear curve fitting. So the non-linear curve fitting doesn't have any relationship with multiple regression. That is what we'll be looking at. Now, the non-linear curve fitting will be a topic for another day. The multiple regression will also be a topic for another day. So we are considering linear curve fitting and linear regression for today. We are fitting a straight line. So permit me to go straight to solve a particular problem and see how we can apply this. Permit me to clean the board so that we can make progress by solving a particular example. Now, for instance, if I have a set of data, you can call it example 1. Example 1 comprises of income X and expenditure Y. The table below shows income X and expenditure Y. Now fit a straight line of Y on X. That means Y, which is the expenditure, is now depending on X, the income. These are things that can be applied or that are applicable to real life. You cannot talk about these things and not link them to solving real life problems. They help us to solve real life problems and interpret results and also forecast or predict or estimate into the future. So now, permit me to write out the data. We have our X, we have our Y. So for the X, we have 10, 11, 12, and 12. Then for the Y, we have 5, 6, 4, 3, and 3. Now you can see in statistics or in numerical analysis, there is what we call visual inspection. Inspecting these two sets of data, X is for income. You can see the income is higher in value. Then Y is for the expenditure. You can see that as X is increasing, Y is decreasing. That tells us something. X is increasing from 10, 10, between 10 and 10. Y is 5 and 6. Of course, there is a bit shift, but from 11 down to 12, there is a steady decrease. That tells us something. We will come back to that at the end of the class. Now, what we intend to fit is y is equal to a plus bx. And this will now give us our normal equation to be summation y is equal to na plus b summation x. Summation xy is equal to a summation x plus b summation x square. So you can call this equation 1, equation 2. We are coming back to that. Now it is this normal equation, we are using the method of least squares. We have generated the normal equations in an easy way. Now you can see we need summation xy. Of course, the number of observations here, n, will be 1, 2, 3, 4, 5. So n will be 5. So we need our summation x, and of course summation x here, if you sum this, 10 plus 11 plus this will be 55. This will be 55. Then if you sum your y, the 6 plus 5 plus 4 plus 3 plus 3 will be 21. Then definitely we need another column. We need our x square, because we'll be needing summation x square. So x is, the first value of x is 10. 10 square is 100. 10 square is 100. 11 square is 121. 12 square is 144. 12 square is 144. 12 square is 144. And when you take the sum of that, 100 plus 100 plus 121 plus 144 plus 144, you are going to have 609. Then again, we need another column. So the sum of this one is 609. So the next one, we are going to have our xy. So we need the sum of xy. So 10 by 5 is 50. 10 by 6 is 60. Then 11 by 4 is 44. 12 by 3, 36. 12 by 3, 36. So you say 50 plus 60 plus 44 plus 36 plus 36 is 226. Now we have been able to get that. So you can see how we have been able, from the normal equations, we have been able to create a table. Now this simply means that these normal equations will now become, look at it, we start from here, our NA, this will be 5A plus B summation X, summation X is 55 plus 55B is equal to summation Y. Summation Y is 21. You call this equation 1. Then the second one is A summation X. Our summation X is 55. So we say 55A plus B summation X squared. Summation X squared is 609 plus 609B is equal to summation XY. Our summation XY is 226. You call this equation 2. Now we have gotten a system of linear equations having two equations or two unknowns in two equations. Of course, we can solve this using the substitution method. We can solve this using the elimination method. So permit me to use the elimination method. I want to use the elimination method to eliminate A. If I'm to eliminate A, you are going to multiply this equation 1 by 55 so that A and B will be of the same value. Then you are going to multiply equation 2 by 5. So that is what we are going to do to eliminate A. So if you have that 55 by A, you are going to have, permit me to rule this, you are going to have 275A plus 3025B, and that is now equal to 1155. That's what you have there. So when you use 55 to multiply 5, you have 275. 55 by 55, you have 3025. 55 by 21, you have 1125. Then using 5 again to multiply 55, you are going to have 275a plus. Now you are going to say 5 multiplied by 609. 5 multiplied by 609 is 3045. So you're going to have 3045b is equal to, then 5 multiplied by 226 is 1130. We're going to have 1130. So now we want to eliminate. For us to eliminate a, we are going to subtract. For us to eliminate a, we are going to carry out subtraction. We are going to carry out subtraction, and after doing the subtraction, a value for a will come out cheaply and easily. Now if we come 275a minus 275a, this will be 0. 3025b minus 3045b, this will be minus 20b, is equal to 1155 minus 1130. This will give us 25. So this means that from here, our b will be equal to 25 over, we are going to have minus over 20. So that's going to be minus 1.25. So our b is minus 1.25. So putting b into equation 2, comma, we have, so putting b into, or let's say even into equation 1, okay, let's put it into equation 1, not equation 2. We have, now look at equation 1 here. It means 5a plus 55 into b is minus 1.25, and that is now equal to 21. So 5a alone will be equal to, when you multiply this, it will be 21 plus, now when you say 50, of course this will now be negative. When crossing to the other side, it becomes positive. So 55 multiplied by minus 1.25 will now be minus 68.75. When it crosses to the other side, it becomes plus 68.75. Plus 68.75. And when you add that together, 21 plus 68.75 to give you 89.75. So this will be 89.75. So a alone will be equal to 89.75 divided by 5. When you divide 89.75 by 5, you are going to have 17.95. 17.95. That's what you are going to get. You are going to get 17.95. So beloved, you can see that we are making progress. Permit me to clean the question so that we can write out permit me to clean this part so that we can write out the model neatly. So the model yc is equal to a plus bx becomes y subscript, that means the estimated y. Some authors write it as y hat, some others call it yc, so they are both estimated values of y. That is what it means. So this model is used to estimate y. It's now equal to, what did we get as our a? Our a is 17.95. Then of course plus b. What is our b? Minus, so it will now be minus 1.25 then the x is there. So this is our linear model for this set of data. Now it doesn't stop there. It doesn't stop there. We want to predict, we want to forecast. We want to predict, we want to forecast. And we want to calculate what we call residual. There's what we call the observed value of y. These are the observed value of y. 5, 6, 4, 3, 3. These are the observed value of x. 10, 10, 11, 12, 12. But now we want to use y because y is depending on x. When a particular value of x is known or given, then we can predict or estimate that the corresponding value of y. So permit me to clean this part of the board so that we can have space to continue with our prediction, our estimation. Now it's time to estimate. Estimation, stroke prediction, stroke forecasting. So we want to carry out this now. We want to carry out this. Now, let's choose a value of x. When x is equal to 11, what will be the value for y? So our yc will be equal to 17.95 minus 1.25 into 11. So x is 11, x we assume the value there. So when you now come here, you now say 11 multiplied by 1.25, then you subtract it from 17.95. You are going to have yc is equal to 17.95 minus 1.25 times 11. You are going to get 13.75 minus 13.75, and that will now leave you in 4.2. You see that? That will leave you in what? 4.2. Now, the residual, our residual is given as y minus yc. Now, for the observed values, let's look at it. There is this value of y here is the observed value of y that came with the raw data. This y subscript c is the estimated value of y. Now, let us go. When x is 11, what is our original value of y? 4. I come again. When x is 11, what's our original value of y? 4. When x is 10, what's our original value of y? Is 6. So this simply means that our original y, or the observed y, is when x is 11, corresponding value of y is 4. And the estimated y that we got is 4.2. So this will be equal to, it will now be equal to our residual is equal to minus 0.2. You see, that is the error term in that particular value, the residual. So, having this, you can see that we said that our b, let's go to the interpretation of the b. We have not interpreted it. Our b is equal to minus 1.25. Remember from the introduction, b is the slope, and b can either be positive or negative. Now you can see that b is what determines the nature of the relationship between the two variables x and y. Our two variables here are income and expenditure. Now the x is the expenditure, the x is the income, while the y is the expenditure. The expenditure is depending on the income. So the x is our income, the y is the expenditure. Now you will see that this b here is negative. That means the slope is going to have a negative impact. That means this particular variable here, x, which is the independent variable, is going to have a negative impact on y, the dependent variable. Y is the dependent variable, the expenditure. So the is going to have a negative impact on it. So that is why you see, I said we'll come back to it. As x is increasing, 10, between 10 and 10, just a little shift from 5 to 6. But then from 4, 11, 12, 12, you can see the decrease. 4, it has reduced from 6 to 4, from 4 to 3. Then when it's 12, 12, it maintains 3. It is now showing in the value of the slope. So the negative value of the slope is showing a downward increase in the value of y. So the dependent variable is reducing as the independent variable is increasing. And this particular value here of b, which is the slope, minus 1.25, has really proven that, has revealed that. So in statistics or numerical analysis, we do first what we call visual inspection of the data. You inspect the data visually, and what you are going to calculate or estimate is expected to be in line with that particular visual inspection of the data. If the data are very large, you may not be able to do the inspection all through from the beginning to the end, but just a glimpse of the data or a flip by flipping through the data, you'll be able to have one or two information. So you can see that as x is increasing, y is decreasing. So it has shown that x has a negative impact on y. Why will x be increasing and y decreasing? And it has shown from the slope negative impact. So the relationship is negative. If it is positive, as x is increasing, y is also expected to be increasing. So a positive increase in x will lead to a positive increase in y. Are you getting me now? So this one that is negative, that means that x is increasing, y is decreasing. That's what we have seen in this value of the slope. So now there is what we call the sum of the residual. If we have the residual is y minus y, so that is the observed y from the data, the original y, minus the estimated y. The sum of it, if I say summation y minus yc, some authors call it y hat, like I said, estimated y, is equal to 0. If this error term is equal to 0, that means that this model, this straight line model, is a model. The model is a line of best fit. If we achieve 0 at this, or very close to 0, that means this particular model we have gotten for this data, it means it is the line is a line of best fit. It fits the data best. That is what it means. So now let us see how we can go ahead and test for this particular value. The question is summation y minus yc equal to 0? Is a question we will answer. If it is equal to 0, the model or the straight line is a best fit for the data set. Now let's go ahead and see how we can carry that out. Now we already have our y here. Now let us calculate our various yc, the estimated y. Then we will now create another column for y minus yc. We can put this in bracket, then we have it this way. Now the first one, of course, we have calculated for 11. For 11, we got 4.2. So this will be minus 0.2. Now let us calculate for 10. When x is equal to 10, our yc will be equal to 17.95 minus 1.25 into 10. Now let us carry out this simple arithmetic. We are going to have 5.45. So the answer will be equal to 5.45. Now let us also do for 12. You know, we have done for 11. We have done for, that means for 10 is, here is 5.45. Then for 10, when S is 10, our YC will also be 5.45. Now let us also do when X is equal to 12. When S is equal to 12, so our YC, estimated Y, will be equal to 17.95 minus 1.25 into 12. So you carry out that arithmetic, you are going to have 2.95. So you are coming here, you are going to have equal to 2.95. So you come here, for X is equal, when S is 12, you have 2.95. When X is 12 also, 2.95. Now we want to go ahead to get the residuals. We want to go ahead to get the residuals. We want to go ahead to calculate the residuals and see what will become of the residuals. Now, if you come here, the first value of Y here is 5. So 5 minus 5.45, this will be equal to minus 0.45. The next one is 6. The first value of Y, the next value of Y is 6. 6 minus 5.45. 6 minus 5.45, that will give you 0.55. 0.55. Then 3 minus 2.95, that will give you 0.05. 3 minus 2.95. 3 minus 2.95 is also 0.05. Now let's go ahead. 0.05 plus 0.05 is 0.1. 0.1 minus 0.2 is minus 0.1. Plus this, it will be minus, it will be plus 0.45 minus this, you are going to have 0. So yes. So you come here, you now say yes. Summation Y minus YC is equal to 0. The model is a best fit. The model is a best. The model is a best fit for the data set. So you can see that the error, the sum of the residual is 0. So the sum of the residual is 0. So this model is the best fit for this data set. So we can also go ahead and also continue to use the model to forecast. Now X, look at it now, X stops at 12. Let us predict the value for Y when X is 13. You can also come and you see when X is equal to 13, you are going to have estimated Y is 17.95 minus 1.25 into 13. When you carry out 13 into that, you are going to have YC when X is 13 is 1.7. So YC is equal to 1.7. You can see that 1.7. So 1.7. So you can see that when X is 13, our estimated Y is 1.7. Look at it now. It's reducing. For the next value of X to be 13, look at it. For the next value of X to be 13, Y will now reduce to 1.7. So you can see that as X is increasing, Y is decreasing. That this is as a result of the negative value that we have for the slope. So beloved, I believe you have you have learned something today. Thank you for waiting patiently to the end of this class. You have been able to see the relationship between linear regression and linear curve fitting. What a good combination of numerical analysis and statistics. You can see the great relationship that numerical analysis has with statistics. What a great blend. So in our next class, we'll be coming up with what we call linear correlation analysis. We're looking at rank correlation and the other correlation formula. We'll be comparing results from the two formulae. We'll be looking at linear correlation analysis in our next class. So please, anytime the video is uploaded, watch out for it. And I believe you have learned how to fit a straight line, how to carry out linear curve fitting, how to carry out linear regression. When you are told to do it for x on y or y on x, I believe you already know what to do. When you are told to carry out regression for y on x or x on y, you know how to do. You know how to start with the model. From the model, you generate the normal equations by method of least squares. Now, of course, our A is the intercept, our B is the slope. The B is what the nature of the slope or the nature of the linear regression is determined by the slope. The slope can be positive or negative. If it is positive, that means the independent variable is impacting positively on the dependent variable. If it is negative, it means the independent variable is impacting negatively on the dependent variable. As we can see in this example of income and expenditure, as the value of x is increasing, the value of y is decreasing. We saw that it can be seen visually from the data set, and we even went ahead to use the regression model, the straight line model, the linear curve, to estimate the value of x when x equals to 13. We got y, the estimated y, to be 1.7, which has reduced from 3 to 1.7. Y has increased from 12 to 13. So once again, God bless you. My name is Dr. Chris Isekaibe, a chief lecturer in a prestigious polytechnic in Nigeria. I'm a numerical analyst, I'm a data analyst, I'm a data scientist. I've shown a blend of numerical analysis and statistics. Please watch my videos, share them in your social media platforms, and as you do, God will bless you. Thank you very much. Thank you and thank you and thank you. Enjoy the remaining part of the day. Bye.